Okay, good afternoon, class. Um, let's continue with um, our topic, whereby we're dealing with we're looking at the average normal stress concept. Okay, this is page 1. Okay, so we have here this particular question is saying that the beam supported by rods AB and CD that have cross-sectional areas of 12 millimeters squared and 8 millimeters squared respectively, if the distance between A and this normal force of 6 kilonewtons, determine the average normal stress in each rod. Okay, so what I would like to do is let's take it step by step. And what is the question really asking us? So we have the structure that's being supported by being supported by rods at point B and at point D, right? So these rods are undergoing some kind of stress because it has to be able to hold up this particular beam here and this force right here, okay, located at 1 meter away from A. Okay, so let's look at our step. What's the first thing you'll do in terms of trying to find a solution? We want to be able to draw our free body diagram. Okay, and in doing so, we can actually replicate the drawing, right, whereby we have force AB, force CD, okay, and then we have this 6 kilonewton force coming, and this is A and this is B, and then we can just draw the span at which these loads are being located. And this is 2 meters, okay, because the whole span is 3 meters. Okay, so that's step number 1. So step number 2, we can use okay, we want to be able to find force AB and force CD, right, using equilibrium equations. Okay, so looking at that, we can take the moments about point A, right? Okay, we take the moments about point A. I'm taking clockwise to be positive. I have 6 kilonewtons times 1 meter minus FCD over 3 meters, right, equals 0. Therefore, my FCD happens to be 2 kilonewtons. Okay, then I can do some of the forces in the y direction. I'm taking upward to be positive. Then I'm going to have positive FAB minus 6 kilonewtons plus force CD equals 0. And I solve for force AB. I'm going to get 4 kilonewtons. Okay. And then once I've found my forces, right? So step 3, I need to be able to find the stress, or the normal stress, the average normal stress in rods AB, right, and CD. Okay, so you know that the normal stress for AB is going to be the normal force AB divided by this cross-sectional area of AB. You know the force of AB was 4 kilonewtons, and it can also be written as this, divided by the cross-sectional area was 12 millimeters squared. So if you convert that to meters, right? Okay, and then over 4. This is going to give us 333 megapascal. So that's the average normal stress of AB, rod AB. Now, to take it a step further, you want to be able to find the average normal stress of rod CD. Okay, equals FCD divided by the area CD. Okay, and that's going to equal, that was 2 kilonewtons divided by 2 kilonewtons here, the force FCD divided by the area, which is pi over 8 times. I'm sorry, I made a mistake here. They already gave us the area, right? They gave us the cross-sectional area. They gave us the cross-sectional area, so we don't need to actually do this part. Okay, this is going to be, since the area was given to us, the area was already given to us, that's going to be 12 times negative 6 millimeters squared. Okay, and when you do that, let's just double check, make sure, divide that by, yes, okay, and this is going to be, okay, this is going to be 8 times 10 negative 6 millimeters squared, and that's going to give us, it's going to give us 250 megapascal equals the normal stress in rod CD. Okay, so just want to kind of go through that section again before we move on. Kind of let me know if there's any questions. Thank you very much. Let's move on to section 6. Okay, here we're going to be talking about a slightly different topic, and it's going to be allowable stress design. So when you go into section 6 of chapter 7, it typically talks about safety. The idea of this chapter is typically how do you design a structural or mechanical member whereby you can ensure safety. And that means that you have to be able to apply it at a load that is way less than the load that will cause it to fail. Okay, so it's very important that if the load that you apply is greater than what you designed that structural member to carry or handle, that member is going to fail. Okay, and that is not something that you typically want. Okay, so in addition to that, you designed the material to be able to handle a certain type of load. Another aspect of failure analysis is to consider the fabrication, how it was made. Okay, you also want to consider any kind of vibrations if there's any available. You want to avoid any kind of accidental impact, You also have to consider atmospheric conditions, so you can try to avoid corrosion. So there are a host of things that you typically have to look at, but this particular section really focuses on the mechanical aspect of things, which is the load part. So in doing so, we implement what you know as a factor of safety, okay? And this helps us to ensure that we can avoid any kind of catastrophe mechanically. And the factor of safety really looks at the ratio of what is it going to take to fail the product versus what's allowable, okay? So for our known terms that we've been looking at, the normal stress and the shear stress, this is our normal stress, this is our shear stress, okay? It has a shear force, it has a normal force for the normal stress. The factor of safety for both criterias or both concepts will be sigma, which is our normal stress, that's a sine of the fail divided by the uh, normal stress allowable. Likewise for our shear stress, this is our shear stress criteria, we have the shear stress failure divided by the shear stress allowable. Okay, so just kind of keep these concepts in mind, and let's kind of move forward. Okay, um, so and again, you know, these shear forces and normal forces, they behave differently on a material. Again, a normal force acts perpendicular to the actual area of the structure. A shear force acts parallel to the actual uh, material, okay, the cross-sectional area. So it's very good to know um, how, how these forces, how they work on a particular structure. So when we come to looking at the, say for instance, a shear stress, for example, say if you have this bolt that's supposed to hold down plate plate 1 and plate 2, and if you add a load, a force, let's say a normal force on each side of the plate, so you're pulling it this way, you're pulling it this way, it wants to shear this bolt, okay? So here is a perfect combination of you having to deal with different types of forces acting on one structure, okay? So let's before we go into an example, I just want you to keep in mind that when you are actually designing a structural member, okay, for strength, is really based on selecting the allowable stress, okay, with a shear or normal stress that will enable it to be able to provide some kind of safety for the intended load. Okay, again, you don't want to design something that's going to fail once it's being um, used. Okay, so let's look at this this example problem in our textbook. Okay, whereby we have a control arm. Okay, this is going to be. We have a control arm, all right, that's subjected to the load shown below. So we have a control arm, we have a force, we have this force acting on it here, acting at an angle here, okay. Um, to determine the nearest quarter of an inch, um, the requirement diameters for steel pins at A and at C, if the factor of safety for the shear is 1.5 and the failure shear is, that happens to be this is 12 KSI. Okay. Okay. So again, they've given us here that at C it's expressed as a double shear, and at A we have a single shear. And again, if you don't remember what a double shear or single shear is, I highly recommend you go into the previous video to kind of understand what those two mean. Okay. So our first step really is you want to be able to draw a free body diagram. Again, we want to be able to design this structure, this control arm, but we need geometry plays a very important role when it comes to designing the materials and where those materials or structure materials are going to be used as far as application. So we need to find out what will be the appropriate diameter of these pins, considering that they're going to experience some kind of double shear here and a single shear here. What will be the minimum or the minimum diameter that is acceptable for this kind of design? Okay. So let's start off with our solution. We want to be able to draw a free body diagram first of all. Okay. Okay. So we can do that, and we can come here. Okay. So we know that we have a load here. This is 5 kips. But we know that it's going to have 4/5. Okay. Let me come here. And we have 3/5. Okay. So this force is broken up into its X and Y component. And we have a force AB here. Okay. And we have a pin that is experiencing two reactions. Okay. And then we have another load here. And then we can draw the span. And this is 3 inches. This is 2 inches. Okay. And so now what we can do is, and again, keep in mind that pin A is experiencing a single shear, while pin C is experiencing a double shear. Okay. So we can now go to this allowable stress design. Okay. So now we can take it a step further now, and we can find out, okay, for our step 2, we want to be able to find the forces, right, acting on pin A and pin C, right? And we can do that by using our equilibrium equations. Okay? So let's start with some of the moments about point C. Okay? So we're right here. This is our point of interest right here. And we have this right here is going to be 8 inches. Let's get rid of this. Okay. And now we can say some of the moments above point C, and that's going to be negative FAB by 8 inches plus 3 kips by 3 inches plus 3/5 times 5 kips times 5 inches equals 0. And then we get our FAB happens to be 3 kips. Okay? Or if you want to say that's 3,000 pounds. Okay. Now we can utilize another equilibrium equation. So the forces in X direction, we taken from left to right to be positive. So all the forces in X direction, and that's going to be negative FAB, right, minus our CX plus 4/5 times the 5 kips, okay, equals 0. And then our our CX, because we define the force at CX, our CX happens to be 1 kip, 1,000 pounds. Sum of the forces in the Y direction equals 0. I'm taking from bottom to top, and that's going to be positive. Okay. When you look at all the forces in the Y direction, you have 1, 2, 3. 3 forces. And they are as follows. Okay. We have CY minus 3 kips minus 3/5 of 5 kips. Okay. And equals 0. And then our CY happens to be 6 kips, or 6,000 pounds. Okay. Now, if we want to now find the resultant force acting on pin C, since pin C, experiences some kind of double shear, we need to find the resultant force at pin C. And that's going to be square root of CX squared plus CY squared. Okay. Let's change let's change the drawing a little bit. Okay. And we can go so when we do that, we find out that our FC happens to be the square root of 1 kip, 6 kips squared, and then FC happens to be 6.1 kips. Okay. So once we find that out, now we can take it a step further and say, in terms of our step 3, we want to be able to find the allowable stress here. Okay, at each pin. Okay, so for pin A, we know that our shear that's going to cause it to fail, they've given it to us to be 12 KSI, right? With a safety factor 1.5, right? So we can say here this we can see here that our formula for factor of safety happens to be what? The shear failure over the shear allowable, right? We can rearrange this because they want us to find the diameter, right? So the tau allowable is going to be the tau that caused it to fail, the shear that's going to cause it to fail, divided by the factor of safety, and that's going to be 12 ksi divided by 1.5. Okay. Therefore, our tau allowable equals 12 times 10 to the third divided by 1.5. And what does that give us? That's going to give us 8 ksi, or if you want to say 8,000 pounds, either or. Okay. I'm sorry, not pounds, but pounds per square inch. PSI. Okay, so that's going to be our tau allowable. Okay, or allowed. Okay, so once now we found that part, we can now move forward and say, okay, that our tau allowable happens to have a shear force V over the area of the pin, which would be pin A, right? Now again, the diameter is what they want, so the diameter resides in the area, so we have to rearrange this and say A, which is our area, equals our shear force divided by our tau allowable. Okay, mind you, we already found tau allowable, right? And that's right here. Okay, so kind of keep that in mind. So our area can be written as pi d squared over 4 equals the shear force over the allowable shear stress. We solve for d, so d happens to be 4 times the shear force divided by pi times tau allowable. Okay, and now that's d squared. Now d would take the square root of both sides, and we have the square root of 4 times the shear force divided by pi times tau allowable. Okay, so now we can solve for dA, which is the diameter of pin A, happens now to be 0.75 inches. Because you know what V is, you know what this value is, you know what this value is, you can plug it in. So that'll be a great exercise for you guys to do. Okay. Now at pin C, all right, pin C again experiences a double shear. Okay, and typically what that means is we know that our resultant force at C was 6.1 kips, so it's going to have a shear force here and a shear force here. So we know that our shear force, because if we do some of the forces in the y direction, equals 0, we're going to have 2v minus our f, which is f sub c equals 0, right? Our v have here, our v happens to be f sub c divided by 2. This is our shear force. Okay, v. Okay. So, and this is page 7. Okay. So now, what we're going to do now, move forward in terms of finding out what is going to be the diameter for pin C, which experiences a double shear. Okay, so we found out that our tau allowable, right, is going to be, from the previous example, K 8 KSI. Okay, now we know that for the allowable, the formula is going to be your shear force at pin C divided by the area, the pin of area, the area of the pin, which is pin C. Okay, so we want to be able to find the diameter, right? So we can rearrange this and say our VC divided by tau allowable. Okay. Now again, our pi d squared over 4 happens to be V sub C, which is the shear force at pin C divided by the allowable. Okay, we solve for D. Again, we're going to get 4 times V sub C divided by pi times tau allowable raised to the power 1/2. Our D sub C, which is the pin, the diameter of pin C, again, that's going to give us 0.75 inches. Okay, so kindly that's the answer there, and this is the answer here. So kindly look at this and let me know if you have any questions. Again, geometry makes a big difference. You don't want to use a geometry that's going to be slightly smaller than intended purposes, because now you're going to have some issues, and you don't want to create a slightly larger diameter where now it's going to create more problems if anything was to go awry. Okay, so understanding how geometry works in terms of the efficiency of building structures and operating structures is very important. Okay, so the takeaway really from this is um, the calculated diameters, right, would prevent failure, at least from a mechanical standpoint. Again, we're not considering vibration, we're not considering any kind of atmospheric conditions like corrosion. We're not considering any kind of misuse of the part, but in terms of just the calculations and the size, diameter, or the size geometry that is needed for this intended application, we've satisfied that by this exercise that we've done here. Okay. Now let's move on. Just kind of give you another example. Okay. Let's give you another example. This will be page 8. And this will be allowable stress design. Okay. Today's date is 10 September. Okay. So here, we are asked to, like, if the allowable tensile stress of wires AB and AC is 200 megapascal, determine the required diameter of each wire if the applied load is 6 newtons. So we have at point C here, it's fixed to a wall. At point B, it's also fixed to a wall. And we have these wires, okay, and some load, 6 kilonewtons, is pulling on this wire. Okay. So they kind of give us the geometric location of the wire. So tell us this is like 45 degrees, and this is a 4 by 3 by 5 triangle. Okay, so we need to know what will be the required diameter to kind of keep this structure at a safe operation. So our step number one, okay, again, it's a tensile stress, allowable tensile stress. Okay, this is the allowable tensile stress, meaning that the 200 megapascal, this structure would not fail. Okay, anything above it definitely will make it fail. Okay, so at 6 kilonewtons, allowable stress of 200 megapascals is very comfortable to operate the structure in a safety mechanism or safety manner. Okay, so if you want to be able to find the diameter, which is similar to what we did previously, let us just start off with our free body diagram. Okay, and we have a force of 6 kilonewtons pulling down, and we have forces that can be resolved into x and y components. This is FAC, and this is going to be 3/5 FAC. This is going to be cosine 45 FAB, and then this is going to be 4/5 FAC, and this is going to be sine 45 degrees FAB. Okay, so that's our first step, right? And then our next step would be step 2. You want to be able to use our equilibrium equations to find forces AB and forces AC. Okay, so we can do some of the forces in x direction equals 0. Okay, and you're going to get 3/5 FAC minus 0.7, cosine of 45 degrees is 0.707 FAB, right, equals 0. Okay, now some of the forces in the y direction equals 0. We're going to get 4/5 FAC plus 0.707 FAB, right, minus 6 kilonewtons equals 0. Okay, those are all the forces in the y direction. Okay, and page 9, allowable. Okay, okay, okay. So now we have here equation 1. We have here equation 1, equation 2. Okay, so let's rearrange this. For equation 1, we have 3/5 happens to be 0.6 FAC minus 0.0770 minus 0.707 FAB equals 0. Equation 2 happens to be 0.8 FAC plus 0.707, which is the cosine of, which would be the, this would be the sine of 45 degrees, FAB, and I can take 6 to the other side, that would be equals 6, right? And then what I can do is I'm going to add these two equations together using, remember, simultaneous equation. Okay, If you don't remember, kindly go to a YouTube video and just type in that and kind of give you a refresher. And so I'm going to add equation 1 to equation 2. We know this is going to be 1.4 FAC. These two go to 0 equals 6. Therefore, I can solve for, so it's going to be 1.4 FAC equals 6 kilonewtons. And I can solve for FAC equals, FAC now is going to be equal to 4 it's going to be, FAC is going to be 6 kilonewtons divided by 1.4 equals 4.286 kilonewtons. Okay. So my FAC happens to be 4.286 kilonewtons. Okay. And now, what I can do now with once I found that, I can now find FAB by going to equation 1 and plug in what I found FAC, and that's going to be when you do the math, you're going to get 3.637 kilonewtons equals force AB. Okay. Okay. So you just go back to equation 1. Equation 1 is 0.6 FAC minus 0.707 FAB equals 0. I want to solve for FAB. So what does that mean? That means that FAB happens to be 0.6 FAC divided by 0.707. And when you do that, you're going to get this. Okay. Now, our step 3, you want to be able to find the diameter. Okay. Find the diameter of wire AB and AC. Okay. And in doing so, we know that our allowable stress, right, happens to be force, the normal force, AB, divided by the area of AB, right? Again, we're looking for the diameter, so we have to solve for the area equals FAB divided by the allowable. And we know if we break the area down, we get pi d squared over 4 equals force AB happens to be 3.637 kilonewtons divided by 200 megapascal, right? Because they told us that the allowable, was 200 megapascal, right? And remember that your megapascal, MPa, can be written, MPa is nothing more than Newton per, well, the M is going to be 10, so that's going to be, keep this in mind, megapascal equals 10 to the 6 Newton per meter squared. Okay, so if you do the math, our D, the diameter of D, wire AB, the diameter of wire AB is going to be 0.0048 meters. Okay, and that's your answer. Right? And likewise, when you do for wire AC, for the wire AC, the diameter, when you do the math, DAC happens to be, again, 4 times FAC divided by pi, that's allowable, and it happens to be 0.0052 meters. So our DAC happens to be 0.0052 meters. Okay, and this is your answer. Okay, so I hope this helps. Thank you very much for your time. I'm very grateful. I kind of went overboard, 45 minutes. Thank you very much. I'm very grateful. Thank you.